Hi students, this video is going to start chapter 5 where we cover polynomial functions. We've already talked about quadratics quite a bit, and we're going to see some higher degree polynomial functions. They can get a little tricky to factor, but we have some techniques to kind of figure out what their factors are. And we also have techniques to find where they cross the x-axis and whether they're above or below the axis and their end behavior. And all of this is going to allow us to figure out what the graph of these polynomial functions looks like. So here in 5.1, we're going to do an intro to polynomial equations and their graphs. We're going to talk about what a zero of a polynomial is, and we're going to graph some factored polynomials. We're going to solve polynomial inequalities and find zeros of polynomials. So in layman's terms, what we're going to learn is how a function behaves as x goes to positive and negative infinity. Okay, we call this the end behavior. And this is completely determined by the leading term. Okay. We're also going to find where the function crosses the x-axis. These are called the zeros or the roots. Okay, this is where y equals 0. Remember, that's what the x-intercept is. It's where y equals 0. This is easy to see if our polynomial is completely factored, which is why we need to know how to factor these higher degree polynomials. Once we know where it crosses the x-axis, then we want to figure out where it is above or below the x-axis. So basically, we just test the intervals between the zeros to figure out if it's above the axis there or below the axis there. So zeros of a polynomial, it's possible that the zeros are real numbers, rational numbers, or irrational numbers, meaning they have like square roots in them, or even complex numbers. Okay, a complex number, if a complex number is a zero, it doesn't actually cross the x-axis because it's complex. It's not in this two-dimensional plane that we graph. But anyways, a number is a zero of the polynomial function p of x if the function evaluated at that value k is equal to 0. That's the same thing as saying k is a root of the polynomial, or it's what it means to say that k is a solution of our polynomial set equal. Okay, so it's just that what values of x make your whole polynomial function equal 0. Those are your roots. Okay, also known as your zeros. Okay, just to define it, a polynomial equation in one variable, let this variable be x, is an equation that can be written in the form sub n times x to the n plus a sub n minus 1 times x to the n minus 1, all the way down to a sub 1 of x plus a sub 0. All these a's, and the reason they have those subscripts is just to let you know which coefficient they are. So each of the a's are just the coefficients to each of our terms, and the n's are the exponents or the degree of those terms. Okay, we always want to write our polynomials like this in descending order so we can see what our leading coefficient is. Okay. So the first thing we want to cover when we have these higher degree polynomials is going to be the end behavior. So there's 4 different ways our polynomial can end. As the x's go towards positive and negative infinity, meaning as you move out away from 0, very, very high numbers and very, very negative numbers, we can go up towards infinity on both sides. We can go down towards negative infinity on both sides, or one side, say as x goes to positive infinity, could also go to positive infinity, and the other side could go to negative infinity, or vice versa. So these are the 4 types of end behavior that we're going to see. And it's going to be all determined by the leading term, okay? So basically, if the exponent or the degree of our polynomial is even, the behavior is going to go in the same direction for both positive infinity and negative infinity. Okay, so if you notice the first two examples, we've got a fourth degree power and a second degree polynomial. When we have a term is a even degree, meaning if we have an even degree polynomial, the end behavior is going to be the same in the positive and negative direction. So it's either both going to go up or both going to go down. Now, in the second two examples, if our polynomial is of odd degree, they're going to go in the opposite directions. So either down and up or up and down. Okay, so that's the first thing to look for, is that the degree of your polynomial will tell you whether your end behavior is going to go in the same direction or in opposite directions. And then beyond that, the sign of your leading polynomial will tell you which of the two it is. So here's how it works. You want to look at your degree. If your degree is even, then if your degree is even, then you're either both going up or both going down. If it's even and a positive coefficient, the end behavior is up in both directions. So as x goes to negative infinity, your y is going to go to positive infinity. And as x goes to positive infinity, your y is also going to go to positive infinity. This is when you are even and positive. Now, if we have an even polynomial, but it has a negative coefficient, that's going to flip everything. So an even polynomial and a negative coefficient is going to make us go to negative infinity as x goes to negative infinity, and it's going to have us go to negative infinity and y as x goes to positive infinity. All right. So if you have even polynomial, your end behavior is the same, whether you're going towards positive or negative infinity in the x direction. And it depends on the sign of that leading coefficient, whether you go to positive infinity or negative infinity. Okay. Now, if you have an odd degree, you're going to go in opposite directions. If you have an odd degree polynomial and its leading term has a positive coefficient, then as you go to negative infinity x, you will go to negative infinity in the y. If its leading term has a positive coefficient, as you go to positive infinity in the x, you will go to positive infinity in the y. Okay. But now if you have an odd degree polynomial like x to the 5, but the coefficient on that leading term is negative, then it's going to flip that upside down and you will go the other direction. Take a little example here over on the left. If we have f of x equals x to the 5 plus 3x squared, and we want to know what its end behavior is going to look like, well, since it's an odd degree polynomial, we know they're going to go in opposite directions. So as x gets really big and x gets really negative, the y's are going to go in opposite directions. All right. And then we want to say, okay, we've got a positive leading coefficient here. So since we have a positive leading coefficient, it means that as x gets big, y will also get big. So as x goes to positive infinity, y will also go to positive infinity, meaning that we're going to go off to the right, top right. And as x gets really small, meaning as x goes towards negative infinity, y will also go to negative infinity. All right. And let me talk about why this is for a second. So when x is really small, like towards 0, when I say small, I mean near 0 here. When x is close to 0, say x is 0, x is 100, x is 1,000, it's close to 0. Then even the small terms are going to contribute to the output, the y value, right? So in this case, let's say x is 1. The first term gives us a 1, the second term actually gives us a 3, and the third term gives us a -1. So all terms contribute pretty much equally. But when x gets really big, let's say x is 1,000,000, the first term becomes 10 to the 30 power. That means 30 zeros. And the second term becomes 3 times 10 to the 12th power, which means 12 zeros. So you notice when x gets large, here it is at a million, it's got more place values, more than twice as many place values as the next term. So you can imagine when x becomes a billion, that leading term is going to just completely overpower whatever the smaller terms are doing. So that's why when we look at end behavior, and end behavior is basically as x goes to infinity, really, really huge, what is y doing? Which direction is y moving? We only have to look at the first term to tell us this. Because when x is huge, the fifth power of x is going to be just so much more than the second power of x that it's just going to dominate completely. Okay, so our end behavior is what happens when x gets really far away from zero, either very, very negative or very, very positive, and it's completely dominated by the leading term. So once we know the end behavior, then what we really want to know is, okay, what's happening in between? So we want to know, where are we crossing the axis and where are we above or below the axis? So what we do to figure that out is we create these polynomial inequalities to figure out where the function is above or below the axis. First, we're going to find where the function crosses the x-axis. So those are the real zeros, or the solutions of our function set equal to 0, right? When y is 0, what is our function equal? And what values, or sorry, when y is 0, what values of x make y 0? Then we just put those values of x on the number line, because that's where it's going to cross the x-axis. And we can split our number line now into these intervals. We just have to test a point in each interval to figure out if we are above or below the x-axis in that interval. Since we know we don't cross the x-axis anywhere else, just one point will do. And then we can write our solution. So let's go through a couple examples here. And I'm going to do these on the whiteboard. All right, so in our first example, we've got a third degree polynomial, x to the third minus 12x squared plus 36x. If we want to find the zeros, the end behavior, and where it's above and below the axis, we can do that pretty easily. And then maybe we'll even try to give it a little sketch. So here's my x and y axis. I can see that we are a third degree polynomial. So I know that the end behavior is going to go in opposite directions. And since it is a positive leading term, I know that as x goes to y will also go to infinity. And as x goes to negative infinity, y will also go to negative infinity. Okay, so that's our end behavior. Now, if we want to figure out what's happening in between, where is it crossing the x-axis, we need to find the zeros. And in this case, we can just factor this guy. We can factor off an x. And then we've got x squared minus 12x plus 36. And that is going to factor to, let's see, that's going to factor to, I believe, is that x minus 6 squared? Yeah, I think that's x minus 6 times x minus 6. And if we want, we can just write that as x minus 6 squared. All right. So our function f of x equals x times x minus 6 squared. So now if we want to find the zeros, we can set our function equal to 0 and just figure out what values of x make our function equal to 0. Well, when x is 0, our function will be 0. And when x is 6, our function will also be 0. All right. So we know that we are crossing the x-axis when x is 0 and when x is 6. I'm just going to put it right there. Okay. So we know 2 points on our function, essentially plotted 2 points of our function. One point is 0, 0, and the other point is 6, 0, right? We know those are both solutions to our original function. Now we want to figure out where is our function above or below 0? And essentially we've got 3 regions. We've got everything below 0, 0, everything between 0 and 6, and everything from 6 on. So we'll just pick any point in this region. Let's pick x equals -1. Let's pick x equals 1, and let's pick x equals 7, just because these are all easy points to put into our graph. And let me clean this up a little for us. All right, so what I'm going to do is I'm going to test each of these points in this interval, in each of these intervals, into our function. So I'm going to evaluate our function at -1, 1, and 7. And all I really need to know is our function greater than 0 or less than 0 in that interval? That's all I'm looking for. All right. So in our first function, we know that whatever is inside this squared thing is going to be positive, right? So we really only have to look at, right, whatever's in the squared is always going to be positive. So we only have to look at this. Is this plus or is it minus? Okay. So that can tell us that our first polynomial, our first solution is going to be less than 0. And our second is going to be greater than 0. And our third is also going to be greater than 0. Okay. So what that tells us is that we are going to be negative in this interval. We're going to be positive in this interval, and we're going to be positive in this interval. That just means the y values are above the axis if we're positive. Okay. So to do that, we can just draw that. We're negative in this very last interval. So I'm going to connect the point that we know we have on a graph to the end behavior we know as x goes to -infinity. Now we're going to be positive in this interval here, but then we have to touch both of these points, and then we're going to be positive in this interval. So that's going to look something like, okay, we're positive, we're touching this point, and then we are positive again and going off into that end behavior that goes towards positive infinity. All right. So let's take a look at what happened. We crossed the axis at x equals 0 because x equals 0 is one of our solutions. We just touched the axis at x equals 6 because x equals 6 is actually, you could call it solutions because we have -6 times another x minus 6 here. Okay. But just to recap what we did, we determined our end behavior using the leading term. Then we found, we factored our equation so that we could find the zeros. And then we tested each interval to see whether it's less than or greater than 0 so that we could figure out where we are on our function in between those zeros. So our sketch was all right, a little weird, but you can see from this image that we got it right. We crossed the axis at x is 0 and we touched the axis at x is 6. Our end behavior is correct and we are correctly above and below the axis where we should be. Okay, so that's how we can use the end behavior and the zeros of a polynomial to get a rough idea of what our polynomial function is going to look like. Let's go on to our next example. All right, so our next example is also a third degree polynomial, but it has 4 terms. So the only difference here is we are going to have to factor this guy by grouping. And I just wanted to kind of do a refresher on factoring by grouping. We'll look at our first 2 terms. They both have an x squared, which leaves us with an x plus 3. And our second 2 terms both have a -4, which also leaves us with an x plus 3. So when we factor this guy by grouping, we've got x squared minus 4 times x plus 3. We can also note that we have the same end behavior as before because we have that the odd degree polynomial, and it's a positive sign leading coefficient. So what do our zeros look like? Well, this thing is going to be equal to 0 when x squared is 4 or x is -3. So x could equal plus or minus 2 and x can equal -3. So we'll plot those on our graph. Here's going to be our -2, -3, and our +2. Right. Then we can just check a point between each of these in our function, and we are going to end up looking like this. All right.